In simple multiplets, all the peaks are separated by the same distance, called the coupling constant, J. To obtain J, measure the distance between two adjacent peaks in hertz. The magnitude of J depends on the strength of the magnetic interaction between the hydrogens and is independent of the external magnetic field. Since coupling is a reciprocal process, the coupling constant for hydrogen A interacting with hydrogens B is the same as for hydrogens B interacting with hydrogen A. Determining which multiplets have the same coupling constant tells you which sets of hydrogens are interacting. NMR multiplets of coupled protons also show a noticeable skewing that distorts the intensities predicted via Pascal's triangle, especially when the multiplets are close to one another in the spectrum. The multiplets seem to lean away from one another, much like the roof of a house. Observing two multiplets that skew in this manner gives additional evidence that the protons of the two signals are coupled. The biggest coupling constants are observed for hydrogens locked in the trans configuration, such as in conformationally rigid cyclohexanes and in alkenes. This large trans coupling constant makes it possible to distinguish between cis and trans alkenes via NMR. Geminal hydrogens on conformationally rigid cyclohexanes also display large J values. Coupling constants of medium size are observed for alkane hydrogens on adjacent carbon centers. Intermediate coupling also occurs between cis-alkene hydrogens, as well as between an alkene hydrogen and neighboring alkane hydrogens, and between orthohydrogens on aromatic rings. Only weak coupling occurs between geminal alkene hydrogens and between hydrogens on conformationally locked cyclohexanes, unless they are both axial. Coupling constants for aldehydes are small, except for alpha-beta unsaturated systems. Coupling constants of less than 1 Hz are difficult to resolve, but lead to a peak broadening. Long-range coupling between hydrogens, 4 bonds apart, can be observed in certain pi systems, such as alkenes, alkynes, as well as between metahydrogens on aromatic moieties. Coupling to more than one other set of equivalent hydrogens leads to complex splitting patterns. In propanol, the methylene protons are split by the methyl hydrogens into a quartet, with a coupling constant of 7 Hz, and each line of the quartet is further split by the aldehyde hydrogen into a doublet, with a coupling constant of 3 Hz. This is a quartet of doublets. If the different sets of hydrogens involved in the splitting have the same coupling constant, then the protons act as if they are equivalent. The NMR signal of the methine proton in 1-chloro-2-methylpropane is equally split by 8 hydrogens into 9 peaks. One characteristic splitting pattern is the pair of doublets observed for para-disubstituted aromatic systems. The 4 aromatic hydrogens belong to 2 sets which are coupled to each other, but only the ortho protons contribute to the major splitting. These doublets exhibit extra lines because of complex second-order coupling that cannot be explained by simple rules. Such second-order coupling is common in aromatic compounds. Second-order coupling also occurs between non-equivalent hydrogens that have very similar chemical shifts. These hydrogens appear in the NMR spectrum as one signal with a complex splitting pattern that cannot be interpreted in a simple manner and is vaguely referred to as multiplet.